Hello guys, good evening to all of you. Yes, Meghna will share. After the class, I'll share that with you, okay? By the way, did you check that on the Learnist? It is uploaded over there. Yeah, you check it once and I'll forward also. That's not an issue. Yes, you will have Kimon test on 27th, I think, the coming Sunday. Okay, just few minutes, we'll start. Okay, fine. So, what have we done last class? Please tell me. Atomic structure, what is the last portion we've discussed, last part? Orbitals you have finished. Okay. Hans rule. Hans rule. Okay, fine. Hans we haven't done, no? Okay, fine. Just a second. Yes. So we had discussed Aufbau principle, and we had also discussed Pauli exclusion principle. Correct. Quantum number we have done. So electronic configuration we have done, right? Well, I'll show you some more here, the examples. Um, okay. So I think I have shown you this thing. Mm, okay, have we discussed this one? I think yes. Yeah, correct. So just let it be aside. We'll take the reference of it. Yes. So let's, you don't have to draw it again. Okay. On the basis of this, suppose, let's see some very simple example I'll just start with. So heading, you write down electronic configuration. Electronic configuration. Suppose we need to write down the electronic configuration of simplest atom I'm taking, hydrogen, then helium, then lithium, beryllium, nitrogen, oxygen, sodium, and magnesium. Okay. Atomic number, first of all, you should know for this. 1, this is 2. Yeah, fine. This will finish it quickly. Just a second. This is 3, 4. Nitrogen is 7. This is 8, 11, and 12. Right. So if you write down the electronic configuration in this order, that would be 1s1. This is 1s2. This is 1s2, 2s1, 1s2, 2s2. It is 1s2, 2s2, 2p, 3, 1s2, 2s2, 2p4, 1s2, 2s2, 2p6, s2, 2p6, and 3s1. Then 1s2, 2s2, 2p6, 3s2. This is the configuration we had discussed. Okay. Now, if you look at the orbital diagram, I'm talking about this, suppose 6 different configuration here. Let us discuss about these 6 configuration here. So we have, suppose this is 1, this is 2, 3, 4, 5, and 6. This 6 different configuration I am taking, and all these are p subshell actually. And p subshell, we know it has 3 p orbitals. So p orbitals, every time it is very difficult to draw the exact shape, that is the dumbbell shape. So we'll take the help of boxes. So one box is one orbital actually. Right? So each of these p subshell has 3 orbitals. There are 3 boxes here, you see. Okay. So this configuration, suppose it is 2p1 configuration. This one is 2p2. This is suppose 2p3. we have 2p4, 2p5, and 2p6 configuration we have. Okay, so because we have six electrons possible in a p orbital, that's why we have six possible configurations: 1, 2, 3, 4, 5, and 6. So this boxes are orbitals. Like for example, this is px, this is py, and this is pz. Okay, so when there's no electrons present into this, then all the three orbitals are said to have same energy, and these are degenerate orbitals, right? When electron fills into the orbital, so it disturbs its degeneracy and the orbital energy changes, correct? So now when you have 2p1 configuration, it means we need to give one electron to these orbitals, right? Since all the orbitals have same energy, whether it is px, py, or pz, so this first electron can go into any one of this orbital. We do not have any control on that. It can go into px, it can go to py, it can go to pz, anyone. Okay, so for reference, usually we'll write x first, then y, and then z. So we always fill this electrons in the boxes from the left hand side. Okay, and we write the electrons here as this. So we have one electron, it is considered to have clockwise orientation, so up-headed arrow. One electron is this. Okay. If you try to fill one more electron into this and the configuration becomes 2p2, then this electron will go into which orbital? Could you tell me? In 2p2, one electron will have here, and the other electron will go into the next orbital, which is this. Remember, one orbital can have maximum 2 electrons, but then also the second electron won't go into this orbital, it will go into the next orbital, right? Third one also the same thing, 1, 2, 3, right? This is 3. If you have 2p4 configuration, then first electron occupies all the orbitals one by one, and then the pairing starts like this. Here also, first it occupies all the orbitals, then pairing starts like this. It occupies all the orbitals here, and then the pairing starts like this. Okay, so the pairing of electrons takes place once all the orbitals belongs to the same subshell is singly occupied. This rule, we call it as Hund's rule. Hund's rule, right? So write down this rule, the statement here. In an orbital, in an orbital, in an orbital, pairing is not done, pairing of electron is not done. In an orbital, pairing of electron is not done unless all the orbitals belonging to the same subshell all the orbitals belonging to the same subshell are singly occupied, means one electron each. Yes, I'll repeat, wait. In an orbital, The pairing of electron is not done unless all the orbitals belonging to the same subshell are singly occupied. Okay, singly occupied. This is Hund's rule, right? Pairing is not done unless all the orbitals have one electron each in the same subshell. Okay. Now, could you write down the electronic configuration of argon? Argon has 18 electron. Calcium has 20 electrons. Then we have phosphorus, 15 electron. Some more we'll discuss. We can have iron, 26 electron. Then we can have chromium, 24 electron. And then copper. Copper has 29 electron. Draw the electronic configuration for all these. Argon, calcium, phosphorus. Argon, calcium, phosphorus. And then we have iron, chromium, copper. Try. Done? Okay. The next three are, we have chromium, copper, and iron. Okay, let's discuss this. Okay, Prakul. Okay, so argon we can write 1s2, 2s2, 2p6, 3s2, 3p6. That is 18 inert configuration. Okay, this one is 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2. 1s2, 2s2, 2p6, 3s2, 3p, 3. Okay. Now, this one is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. The copper is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4, and this one is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. Okay, so this is the electronic configuration, if you write, correct? So some of you or most of you have written this is the electronic configuration we have, right? So no, we'll write 4s always first because 4s has lesser energy than 3d. Okay. Now in this, there is a correction here. And the correction is what? And the correction is what? This particular thing is not correct. This one is wrong. And instead of this, the correct electronic configuration in the last we have, it is 4s1, 3d5. It has exceptional configuration. Similarly, here also, this one is not right. And it converts into, again, 4s1 and 3d10. Okay. So yes, the next question is, why does this happen, right? The reason is, you see the 3D subshell, right? 3D subshell has 5 orbital, D subshell has 5 orbital, in fact, 1, 2, 3, 4, and 5. Okay. So, and 4s has, if you write down this orbital configuration of it, this is 4s and this is 3D. So it has 2 electron, 4s2 initially, 1, 2, 3, and 4. But suppose if one of this electron jumps here into this orbital, right, then the configuration becomes 4s1 and 3d5. Right, it is 3d4, it is 4s2, this becomes 4s1 and 3d5. Now this configuration, you see 3d5 and 3d4, if you compare, this one has symmetrical arrangement of electron. All the orbitals are singly occupied. So it is symmetrical arrangement, and this gives the symmetrical arrangement of electron. It gives extra stability to the atom. That's why this configuration is more stable, and this one we do not have, but from 4s to 3d, it is possible in this only, s to d only, right? S to p it is not possible, but because the energy gap is high over there. No, 4s is more still. What do you mean by this? I don't get you, Shraddha. What do you mean by 4s is more stable than 3d? No, 4s has lesser energy and 3D has little more energy than 4s. That's fine. But the energy gap between 4s and 3D is not that high. That's why from 4s, the electron transfers or shifts into the 3D shell if overall it is getting more stability. So if this happens, overall the stability of the atom increases, and that is why it is happening. Okay. Yes, Dev, yes, that's right. Same thing happens in this also. If one electron jumps here, all the electrons are completely filled. So this is fully filled configuration here. So here this one has fully filled configuration. It is this one is half filled configuration. And hence the fully filled and half filled configuration has extra stability and it is more stable. Hybridization, let it be Prakul. We won't discuss hybridization now. It is a different thing. You won't get it. Because hybridization is we define in bonding state. We are not talking about bonding now. So let's not go over there. Yes, in S and P, it is not possible. I'll give you one example. Suppose we have carbon, right? Carbon electronic configurations, if you draw, carbon electronic configuration, if you draw, carbon has 6 electron. So it is 1s2, 2s2, 2p2. So here it is not 2s1 and 2p3. This is not possible because in S and P orbital, the energy gap is high and it is not that easy for this s electron to jump into the p subshell. That's why this kind of transition is not possible. This transition is only possible between S and D, like this we have 4s 3D or 5s 4D, like that. No, that's not. It's not possible with D and P also. See, actually, no, it's not possible in S. Only S and D it is. See, actually what happens, we have 3s orbital, then we have 3p orbital, then 3d orbital, and then we have 4s after this. So this two transition is possible, 3d and 4s. But this S and P, the energy gap is high between these two. It's a factual thing, and hence the transition is not possible. Yes, only these two cases we have exception, chromium and copper, and that is why it is very important. No, not possible for S2F also. Only from S to D. Okay, understood? Okay, can I move on? Tell me, guys. Yes, and one more thing, it happens on its own, right? We are not doing anything here. Electron itself goes into 3D. It's not like we are making this shift possible. No, in Fe it is not possible. How it is possible in Fe? It is 3D6, it is not possible here. Okay, let's move on to the next thing. Now, when you do this, based on this, you'll have, one kind of question that they ask in the exam, and that is related with the orbital wave function. Okay, I'll just write down here. Orbital wave function, which we have discussed in Schrodinger wave equation. Shraddha, you see, in copper, what happens? We have argon 18, then 4s1, 3d10. How it is possible in carbon? It is argon 4s2, 3d6. How this will get 3d5? It is possible here. Where does this one electron go? S cannot take this electron because already has 2. So it is not possible to have 3d5 configuration. Are you getting it? Yes, whenever you have 3d4, it has tendency to convert into 3d5. Whenever it is 3d9, it has tendency to convert into 3d10. That is it. Correct? Yes, obviously 3d5 configuration is more stable than 3d4. Okay. Now you see this orbital wave function. We know this wave function psi, it gives all the information about electron, right? All the information for an electron. Okay. This psi, it has two components. One is radial component and other one is angular component. Theta and phi. Yes, it's fine because 3d10 gives extra stability to the atom. That's why it converts into 3d10. Meghna. Just a second, I'll discuss this. Okay. So this one is radial component, other one is angular component. So actually you see the electron position, if you try to define, we take the help of polar coordinate here. Okay, we take the help of polar coordinate. Polar coordinate means what? Okay, this is suppose we have the position which can define with respect to this point. Okay, so this point you see, this point you see, it is this distance is r, right? And this one, the angle that is made on the two axes here, right? So this one is suppose phi and this one is suppose theta. So it has two components. One is angular component with the axis, with respect to the axis, and other one is the radial component, that is the distance from the nucleus. Right, so we take the help of polar coordinate here. It is a polar coordinate. However, this you don't have to do anything because you won't get question over all these things. Just it has two component, one is radial, other one is angular. Okay, this radial component, it depends upon what you have to memorize here. This is the radial component, and it depends upon N and L, the principal quantum number and azimuthal quantum number. Hence, it gives us an idea about the size. So it gives us an idea about the size of the orbital. Size. This theta and phi, it is the angular component, right? It is the angular part of wave function, and this depends on L and M. L and M. Hence, it talks about the shape of the orbital. Because once we know L, we know the orbital, and hence we know the shape also. Spherical, dumbbell, double dumbbell, anything, right? So this is the point you have to, 2 points you have to keep in, right? Questions are very simple here. I'll show you what kind of question they ask in the exam, right? But before that, we'll discuss one more concept and then we'll look at the questions. Okay, one thing you must take care of. Sometimes what happens, they'll give you this kind of notation and ask you to find out which orbital it is, right? They'll give you some number like this, psi, and suppose 420, like this they write. And the question is which orbital it is. Right? So these numbers, actually it signifies something. What is that thing you see? Psi is 420 is nothing but N, L and M. So if you compare the two here, the N value is 4, L value is 2, and M value is 0. So with these three values, could you tell me which orbital is this? Which orbital is this? Could you tell me with these three values? Yes, so this is nothing but L is equals to 4, N is equals to 4. So principal major shell is 4. L is equals to 2. It means it is D subshell. M is equals to 0. It means it is Z square. So this kind of question, easy question they ask you. Right. Again, I'm telling you, if you try to understand the actual thing over here, which is beyond our syllabus, right? It is quantum physics. You cannot, understand much thing over this, right? So the basic thing is you should know only the two things here, that wave function has two components. One is radial, other one is angular. And this psi depends upon three quantum numbers, that is N, L, and M. That's why one question, if you remember, I have given you last class that this thing, Schrodinger wave equation gives what all quantum numbers? The answer would be N, L, and M. It is not S, right? S we don't get here, right? So these are the things you have to keep in mind. This kind of question, very simple question. Why not dz square magna? Could you tell me what is M is equal, L is equals to 0 signifies what? L is equals to 2 signifies what? 2. And if D is equals, L is equals to 2, so M value could be anything from -2 to +2. If M is 0, it is definitely dz square. Last class I have discussed. Check your notes once. Is it? Correct. So this is one kind of question they ask here, you must take care of. One more, we have different question here, but before that we have to understand, yeah, it can be anything, X or Y, yeah, Shraddha. So one more concept we have to understand here, and then we'll see that question. And that concept is, write down all of you, the last concept of this chapter, and that is nodal surface. Nodal surface. Definition, all of you write down. It is the surface at which the probability of finding an electron is 0. It is a surface at which the probability of finding an electron is 0. Okay, this is what the nodal surface, we have definition I have given you. Nodal surface, we have two types. Okay, we have two types. The first one is spherical or radial node. Spherical or radial node. A spherical node means the surface is a spherical surface where the probability of finding an electron is 0. A spherical or radial node, and the formula of finding out this is n minus L minus 1. This is the number of spherical or radial node we have. Number of spherical node is n minus L minus 1. The second one is non-spherical node. We also call it as angular node. Right, so number of non-spherical or angular node is L. Okay, the number of non-spherical or angular node is L. So from this two formula, you can easily find out the number of nodes present in any shell. So if I ask you, what is the total number of nodes? What is the answer? That would be n minus, we'll add both here, n minus L minus 1 plus L. So total node is n minus 1. So one kind of question that they ask, okay, so if they ask you the number of nodes, you can directly find out with this formula. Okay, if they ask you number of spherical node, you can use this. Non-spherical, you can use this. That is it, right? Now, one kind of question is regarding the number of nodes. Yes, correct. Yeah, L is the azimuthal quantum number, N is the principal quantum number. Okay, so if they ask you number of nodes, easily you can answer this. This is the two things you need to keep in mind. Okay, sometimes they'll give you graph also, and with the help of graph also we can conclude something, right? So what other things that we can conclude from the graph, that we'll discuss. But first of all, you see, if I ask you the number of nodes for one s orbital, total number of nodes, spherical, angular, both, you tell me. One s orbital, how many spherical node we have? Right, so number of spherical node and number of angular node and total number of node. When you substitute this, n is 1, L is 0 for S subshell is 1 is equals to 0. L is 0, so it is 0. So there is no node for this. Means we do not get any surface around 1s orbital where the probability of finding an electron is 0. There is no node at all, right? Can we say for S subshell, angular node is always 0? Right? Yes, so write down this point, note. Angular node is always 0, or write down like this. There is no angular node for S subshell. There is no angular node for S subshell because L is 0. Yes. Okay. This is one thing. Now, if you see the graph over here, 3 graphs we are going to discuss. Okay. So the first graph we have here, it is for between the wave function psi and the distance r, the radial distance r. This graph we have. The second graph we have between the probability density function, that is psi square, and r, the distance from the nucleus. And this graph, the y-axis is psi square 4 pi r square dr integration, and this is r. So anybody, could you tell me what is this? What do you understand by this term when you write psi square into 4 pi r square dr? What is this term? Integration of it. What is psi square? 4 pi r square r dr. See, I'll tell you. See, this 4 pi r square is the area, surface area. Because we have r square, so it is dimension. If you check, it is our unit is meter square. So meter square is area and into dr, that is the length again. So meter square into meter is meter cube. So this entire thing is volume. Yes or no? 4 pi r square dr is the volume. Is it? Is it? Tell me. Yes. So suppose this is a spherical surface we have, right? And it is the okay. So this is the spherical surface you see, and this is the thickness of this surface. If you can imagine, this is the thickness here. Right. The thickness is dr and the surface area is 4 pi r square. So for this one, if I write down 4 pi r square, this is the surface area of this sphere into the thickness of the sphere is dr. So this becomes the volume of the sphere. Would you agree on this? Tell me. Yes. Please respond, guys. So this psi square into 4 pi r square dr, which is the volume, right? This is the volume we have. And we know it is a probability density, means probability per unit volume. Right? It is probability per unit volume. So this term is the, it is the probability of the electron. Yeah, you can say that, Madhumati. That's fine. Because we have vacant space, empty space within an atom, no? So you can consider that, honestly. Yes, because psi square is the probability density function of an electron. See, psi is related with electron only. So psi square, whatever it gives, psi whatever it gives for electron only. So these three graphs that we have, one is wave function with radius, probability density function with radius, and it is the probability with radius. Okay, probability with radius. So psi and r, the graph that you get here is, and this graph I am drawing for 1s. All these things is for 1s. Similarly, we can have for 2s also, for 3s also. Okay, so 1s, the graph that we have, we get the graph like this. Goes like this. Okay, psi square graph is more steeper. It comes like this and it goes this way. 4 pi square, this is the probability, and this is the nucleus we have. So we know the probability of finding an electron in the nucleus is 0. That's why the probability graph always start with nucleus, goes to a maxima, and then again comes down. But here it won't touch the axis, because when it touches the axis, the probability becomes 0, and that is not a possible case for 1s, because there is no nodal surface here. Did you get my point? Yes. So keep that in mind. This probability graph it would touch the axis, and that point will be equal to the number of nodes here. Since we have no nodes, means there is no surface where the probability of finding an electron is 0. That is why it will never touch the x-axis for 1s I'm talking about. Is it clear, guys? Please respond. Yeah, we'll discuss that, Archit. Just a second. Just focus on 1s first. We'll discuss for other also. Second point, what I'm trying to tell you here, psi and r, psi square and r, how do we get this graph? That you do not ask, you do not think of. Because for that, you must have the relation of psi and r, which is not there in our syllabus. So the pattern just to try to understand, psi and r graph will have like this. Similar kind of graph, more steeper curve will get for psi square and r. And probability graph, you can easily understand, it starts from origin, goes to a maxima, and then comes down, but it will touch, it won't touch the x-axis if it is for 1s. Correct? Let us discuss for 2s. Okay, you will have more clarity on this. Okay. So first of all, guys, you tell me number of nodes for 2s orbital. Tell me, spherical node, how many spherical node we have? How many angular node we have? A spherical node is n minus L minus 1. Substitute the values. Total number of node is 1, right? Remember always angular node is non-spherical, and that we cannot show over the graph, right? Spherical node we can show. Now again we'll draw the 3 graph here. So look at this graph. So this graph is, again the axis is same. It is psi, r, this is also r, this is also r. This is again probability graph, probability axis, psi square, 4 pi r square dr integration, and this is psi square dr, psi square is. Okay, again for 2s, since the node we have one nodal surface here, then this graph will touch the axis once. It goes like this. See this? It comes down, it crosses the x-axis, it goes like this, and then again comes back closer to the axis, but again it won't touch the x-axis here. It will touch only once because we have only one node here, right? Above the axis, we'll write it as positive, and below the axis, we'll write it as negative. Because this wave function can be positive and negative also. So like this it goes. Now similarly, psi square, if you draw, it comes down to the node, which is this. And this square is just exactly the mirror image of this part, which goes like this. It won't touch the x-axis. Psi square cannot be negative. That's why all the graph will be above the axis. If you talk about the probability graph, it starts with origin always, right? And it has one nodal surface. So it comes down, touch the x-axis where we have the nodal surface, right? Again, it will go up and go like this. It won't touch the axis here. So this is what, this is the nodal surface we have. Or simply I'll write down node. This is one node. This also represents one node. And this also represents one node. Tell me, did you get it? No, it won't touch the y-axis. It is like asymptote to y-axis. Clear? Now, if you get a graph like this, usually in the exam or in the question, you'll get probability graph. So you can actually conclude few things from this graph. One is what? The number of peak that you have here, right? So we have two peaks and one node. So number of node is one lesser than the number of peaks in the graph. Sometimes they also ask which graph is correct for this particular orbital. So if it is given that 1s, 2s orbital, then we can have graph like this. Okay, it will have only one node. Remember, this is not a node, this is a nucleus, right? So the number of time it touches the x-axis, that would be the number of nodes we have. So for 2s, it will touch only once the x-axis. This graph won't touch here the x-axis, right? And another thing, obviously this will have certain distance, right? Suppose if I am assuming this distance as r, this distance as r, right? So here also we have the same distance, and this also we have the same distance from the nucleus, r. So what does it mean? It means if you have a sphere, this is 2s, and 2s I am assuming as this, just a second. 2s, suppose I am taking this one. This is 2s. Suppose this is 2s, right? And this is the nucleus. So around this nucleus, we have a spherical surface at a distance r from the nucleus. That spherical surface you assume is this. We have a spherical surface at a distance r. This distance r we have, since it is spherical node, that's why this is spherical surface I am assuming. At a distance r, where the probability of finding an electron is 0 on this surface, right? So this surface, at this distance, we have a spherical surface where the probability is 0. So this is the nodal surface we have. Did you get my point? Yes, that is what it means. Understood? You can type CLR, all of you, quickly. Right, spherical surface we can represent, but angular nodes are non-spherical. This has some weird shape. So those kind of shape we cannot, draw over this 2D, thing, right? That's why angular node we do not show in the graph, correct? So this is one thing. One is, so they'll ask you the number of nodes kind of questions. Other kind of questions, they can ask you some graph related question. They can give you the graph like this, and they can ask you which orbital this graph represents. That is also possible. This kind of question they ask. Okay. Third type of question also possible. I will show you that. But before that, you write down one note here. Write down the note. The probability graph always starts with 0. Or origin, you write down nucleus. The probability graph starts with origin 0. And the number of peak in the graph is 1 more than the number of node. Okay, this is the thing you must keep in mind. Now, another thing, they can ask you, what is the nodal surface for one particular orbital? What, Shraddha, just now that I dictated, that the line that I said just now? I said probability graph always starts with nucleus, that is 0, origin you can say, always starts with origin, and the number of peak in the graph, and the number of peak in the graph is 1 more than the number of node, is 1 more than the number of node. Okay. Yes. Now the next thing, they sometimes they ask you to find out or to answer which is the nodal plane or nodal surface for a given orbital. Right. What I said, nodal plane or nodal surface for a given orbital. Okay. So, for example, you see for 2p orbital, 2p orbital, and suppose I am taking px for 2p. So px orbital, the nodal plane would be the perpendicular plane for this x, that is yz plane is the nodal plane. We always take the perpendicular plane, is the nodal plane. For py, the perpendicular plane is xz, plane is the nodal plane. For pz, we have xy is the nodal plane, right? 2p is this. 3D, this one is important. 3D, if you have 3D orbital or 3D subshell, right? So how many orbitals it has? You see here, if you calculate the orbital here, for 2p, I did not calculate this. The angular node is, the angular node is 1, but a spherical node is 0. 2 minus 1 minus 1 is 0. So we have only one. For px, we have one nodal plane, py another, and pz we have one nodal plane. Similarly, if you find out for 3D, so angular node for 3D is 3 minus 2 minus 1 is 0, but spherical node is L value, that is 2. We have 2 total node here, right? So all orbitals will have 2 angular nodes for 3D. All orbitals for 2p has 1 angular node, that is yz, zx, and xy. So for 3D, if it is dxy orbital, dxy, we know it is in the...
Excuse me, sir.
Yes.
Shouldn't angular node be 2 and spherical node be 3 minus 2 minus 1?
Correct. I've written it by mistake. My bad. This is spherical and below 1 is angular. And this one is angular. Correct. 2 angular node and 0 spherical node. So dxy is in xy plane. The perpendicular plane of this is xz and yz. These 2 planes are nodal planes because we have 2. So we have 2 nodal planes. DYZ, could you tell me what are the nodal planes for DYZ orbital? DYZ, we have XY plane and XZ plane are the nodal plane here. Right, nodal plane. DYZ, if you see, it is YZ, it is done XY, YZ, ZX. We have XY plane and YZ plane is the nodal plane. One exception we have, write down DZ square orbital. DZ square orbital does not have any nodal plane. Does not have any nodal plane. Okay. For DZ square, there is no any nodal plane. And the angular nodes for DZ square orbital are cones. The angular nodes of DZ square orbital are cones. Okay, it is in the shape of cone. Okay, that is one thing you must take care of. DZ square orbital has no nodal plane, but it has nodal cones. It's not a plane, it's a cone. So this is the one thing that you must remember, DZ square orbital. They have asked this thing in the exam. Now, one question for DZ square, there is no nodal plane. There is no nodal plane for DZ square. But the angular node, nodes for DZ square orbitals are cones. Means it is in the conical, in the shape of cones. That is what it means. See, angular nodes means it's just a node. Now this node can be a plane and cannot be a plane. Right, so that's what I'm telling you. For DZ square, the nodes are not a plane. We don't have nodal planes, but we have nodal cones in the shape of a cone. That is it. Arshit, tell me. Done? Okay. Now you see this question here. For hydrogen atom, write down for hydrogen atom, the wave function is given. The relation of wave function psi, it is given. Psi is equals to 1 by 32, 1 by A naught to the power 3 by 2, open bracket, x minus 1, x square minus 8x plus 12 e to the power minus x by 2. This is the relation given for psi and x, where x equals to 2r by A naught. A naught is the first Bohr orbit. First Bohr orbit. Find the minimum and maximum position of radial nodes. Okay, let me explain the question first of all. You see, psi is given in terms of x, and x is a function of r. R is the distance from the nucleus, right? So you see, psi and r, we have this relation given, and the graph that we draw like this kind of graph we get from this kind of relation only. If we do not have this relation, we cannot draw the graph, right? So this kind of relation, how do we get, and what is the relation we have, that is not there in our syllabus, right? That's why this psi and r graph idea we don't get, that how do we get this graph, why not some other shape we can get. So this graph based on this relation of psi and r. Now when you get this question, you will have this relation given, you don't have to worry about it. This relation is given, which is here, and then we need to find out this two things. Try to find out this question. Oh, okay, Pragul, I'll explain this. Wait. Let others try. What happened, guys? Are you getting it? Or should I do it? No, that's not possible, Gayatri. See, I'll give you one hint. Just a second. It's very simple question. It's very simple. You are not getting it probably. Just let me just give you a hint here. Just a second. All of you listen to me, guys. See, what is psi? What is psi? Is a wave function, correct? What is psi square? Probability density function, correct? If, see this, if psi is zero, if psi is zero, it means, can we say psi square is zero? Yes. Okay. If psi square is zero, it means probability is zero. Is it? Probability is zero. And probability of what? Probability of finding an electron is 0. Agreed? Yeah, 0, right? So when probability of finding an electron is 0, it means that particular point, that particular surface is what? Is nodal surface, correct? So we need to find out for what value of r, for what value of this r, this psi becomes 0. In other way, what we can say, find the minimum and maximum position of radial node. When they have mentioned node, it means you have no other choice, but you have to substitute psi is equals to 0. Did you get it? Yes. What happened? I said what? Suppose you have to find out minimum and maximum position of radial node. Radial node means what? From nucleus, just a second, from nucleus, at what distance, minimum and maximum, at what distance we have a radial node, means a spherical surface where the probability of finding an electron is 0. This is what the question is. Okay, minimum and maximum distance, the probability of finding an electron is 0. This is what the question is, if you are getting it right. So like this, we have a spherical surface where the probability of finding an electron is 0. So this distance, these two minimum and maximum distance you need to find out. That is what you have to do, Gayatri, because the thing is we have to find out node and we have to satisfy the condition of node. And what is the condition for node? Psi must be 0. Probability must be 0. Probability 0 means psi square 0. Psi square 0 means psi 0. So you have to substitute psi 0 over here and you have to solve this for x. That is your answer. Did you get it? Tell me. Now try this. That's correct, Weber. That's right. Arshit, Arshit, did you get it? Prakul, tell me. Okay, I cannot take everyone's name. Okay, so it's not like I'm, taking only 4 or 5 names, right? But I'm asking all of you. Please tell me, did you get it? Yes, right, right, right. You have to equate it to 0. You will, Gayatri, you will get answer in terms of A. That's right, Arshit. You'll get answer in terms of A, that is A naught. Okay, so since you have to find out radial node here, so to satisfy this condition, the probability must be 0. And for that, I am substituting psi is equals to 0 in this equation, correct? So when you substitute psi is equals to 0, we'll get x minus 1 and x square minus 8x, sorry, minus 8x plus 12 is equals to 0. This is what the cubic equation you have to solve. That is it. Just a second, guys. Okay. Yes, you. I think 1 and 6 you got in terms of x. X value you got 1 and 6. Right. Yeah, that's right. In terms of A, you need to find out. So obviously, either x minus 1 is equals to 0, or x square minus 8x plus 12 is equals to 0. You solve this, you'll get x equals to 1, and x is nothing but r by a naught. 2r by a naught. So r is equals to a naught by 2. And when you solve this, you'll get x equals to 4 or 3. And when you solve this for r, that would be 2r by a naught is equals to this. So this equals to r is equals to 2a naught and r is equals to 3a naught. Right, so maximum value is 3a naught and minimum value is a naught by 2. This is the answer for this question. Oh, what I have done. I have, oh, just a second. Yeah, it's correct. 6 and 2 will have. Okay, so x value would be 6 or 2. X value is 6 or 2. So r value would be, we'll get here 2r by a naught, 3a naught, or r value is a naught. So three different values we are getting. Answer is the maximum value is 3a naught and the minimum value is r is equals to a naught. Okay. So now the next question, if I ask you here, how many nodes we have for this? How many nodes we have? Number of nodes? Three nodes we have. Why three? Because we are getting three values of r for which psi is equals to 0. Yes or no? Okay. Right. Now suppose this was the question, we have solved this and we see this. Suppose this relation is given in the question, simply this psi relation is given. And if they ask you the number of nodes possible for this relation, how many nodes possible? Right, that is the question. Then how do we do this? You don't have to solve this and find the value of x. Right, you just see this, it is a cubic equation. It means it gives three different roots, right? Three roots it will give, right? Hence we have three nodal plane here. Sometimes what happens, yes, sometimes what happens, you will have perfect square here. You will have perfect cube. In that case, you have to be extra careful, right? Extra careful. But this equation gives you an idea that how many maximum roots, maximum nodal surface possible for this. Correct. One last thing, whenever you see this kind of question, this kind of psi relation it is given, you don't have to do anything, whether you understood this or not. You just substitute psi is equals to 0 and find out some values. You'll get the answer. Because there is no other way we can do in this question. The only one thing is psi is equals to 0 we have to substitute. Depending upon the question, whether they are asking for the number of nodal surface or maximum minimum number, or at what distance in terms of a naught we have a nodal surface. They'll give you four options here, like 2a naught, 5a naught by 7, like this. So you have to choose the appropriate one in this one. So this kind of question they ask in the exam. No doubt, easy this one. Not difficult. Okay, one more question on the similar concept. We'll discuss the last one for this chapter. You see this question? The wave function psi is given, and this is for 2s orbital. It is 1 by 2 root 2 pi 1 by a naught to the power 1 by 2, 2 minus r by a naught e to the power minus r by 2 a naught, right? So at r is equals to r naught, a radial node forms. A radial node forms. Find the relation between r naught and a naught. Yes. Do you need to solve this? Not actually, because we know at r is equals to r naught, we have a radial node, means psi 2s equals to 0. You substitute r is equals to r naught here, we'll get r naught by a naught minus 2 is equals to 0. So r naught is equals to 2 a naught. Okay. One another thing, this kind of question they haven't asked, but I'm going one step ahead from here. If they ask you, find out the radius where the probability of finding an electron is the value, right? So a naught value, we know it is a Bohr radius, right? We know r naught, r is equals to 0.529 n square by z, right? So for n is equals to 1, z is equals to 1, a naught value is nothing but 0.529. So for the given value of this a naught, we can substitute this here and find out the radius at which the probability of finding an electron is 0. Right, the exact value also we can find out by substituting the value of a naught. Okay, is it clear? Any doubt? For if it is for hydrogen atom, we can use that is equals to 1. If it is any other atom, we can substitute it here and find out the value. Yes? Clear. So this is it for this chapter. Atomic structure we have done in so detail. You can solve assignments. It's there on Learnist given. Okay, so we are going to start a new chapter, and that is periodic properties. Which chapter is going on in the school, by the way? Yeah, it is a new chapter. Atomic structure, we are done. Atomic structure is finished. We are doing a new chapter this one. Okay, so they are doing chemical bonding. Have they done this one, periodic properties? Okay. Okay, fine, not a problem. Okay, so the periodic property, you see, this is the chapter where we are going to study few concepts, few terms that will use in entire chemistry actually. Okay, if you remember in the first chapter, that is GOC, that we have discussed, there we have discussed a term that is electronegativity. Remember that? Yes. So electronegativity we are going to study here in this chapter. Okay, this kind of term we are going to understand. It is not a, you know, a chapter of physical chemistry. This is the first chapter of inorganic chemistry, correct? So you're not going to get any numerical question into this. We have theoretical questions, just we have, some trends, some order, some concepts, and then some exceptions into this that we'll see, right? So it is more about, you need to understand the concept, you need to understand the trend, how it goes, right? Along the period, top to bottom. We'll discuss about periodic properties also, and then what are the exceptions we have in this, right? So there are so many exceptions we will discuss here, right? You have to memorize all those. Okay, you cannot skip these things. Okay, so periodic properties is what? So first of all, when we started looking for atoms, different elements, right? Then the challenge is, because we started getting a very huge number of elements which has different properties. So scientists in that era, they started looking for arranging those atoms, elements in a proper way. Okay, what happens in any problem? I got it. Just a second. Okay, fine. So, so when we got to know about various different elements, so we started looking for the arrangement of those elements. Like when once we come to know about this, came to know about this various subatomic particles, electron, proton, neutron, then we started looking for what? The arrangement of subatomic particles, and in that way we got different models that we call it as atomic models. So here also, when we got to know about various different elements, we started looking for the arrangement of those elements so that we can easily understand the properties of those. Means one kind of properties will have a group of that, another kind of properties will have a group of that particular elements. Okay, so in that way there are different theories come up, right? Came up into that, right? The point is, the various different scientists, like Proust has given its own theory. He said all atoms are made up of hydrogen, which was obviously not correct. So we discarded that particular theory later on. Similarly, Dobernair is other scientist. He has given its own theory, right? Newland octave rules, we have another theory. Mendeleev's periodic table, another theory. Lothar Meyer another theory of arrangement of atoms. And the last we get is a modern periodic table, which is a modified form of Mendeleev periodic table, right? So that is how we get the modern periodic table, in which the atoms are arranged in a proper manner, and it is easier for us to memorize the properties of those elements. Correct? So this thing, the discovery of periodic table, it is now, removed from your syllabus. 11th class syllabus is not there, right? The recent changes that they have made, they have removed this particular part into this, right? So I am not going to leave these things completely because it is important for you to understand the discovery, the history behind it. But I'm picking up only the important one on which the question has been asked. Okay. So first theory, the first attempt was made by the scientist called Proust. So quickly we'll finish this off. So write down the first thing. Write down the heading first of all: discovery of or development of atomic model. Sorry, development of periodic table. Write down development of periodic table. One second. Uh, Development of periodic table. The first theory is Proust, Prousts, Proust hypothesis. Right down. According to this theory, all atoms are made up of hydrogen. All atoms are made up of hydrogen atom, which was wrong and hence discarded. Just one line you write down. Which was wrong and hence discarded. This was the first attempt made. The second one was Daubernier triad rule. This one a bit important. On this you'll get questions. Daubernier triad rule. Just a second, I'll repeat. Triad rule. Proust hypothesis is, according to this theory, all atoms are made up of hydrogen. All atoms are made up of hydrogen, which was not correct and hence discarded. This was the first attempt. Next, write down Daubernier triad rule. Write down, according to this rule, according to this rule, in a group of three elements, write down, according to this theory or rule, in a group of three elements, in a group of three elements having similar physical and chemical properties, having similar physical and chemical properties, comma, the atomic weight of the middle element, the atomic weight of the middle element is the mean of the other two. Atomic weight of the middle element is the mean of the other two. Okay. So look at this example. Example you must remember for this. Suppose I'll take three elements: lithium, sodium, potassium. The atomic weight of lithium is 7 and atomic weight for potassium is 39. If you take the average of the two, 39 and 7, you'll get 23, right? And 23 is the atomic weight of sodium. So what we say, these three elements forms Dobrnir triad, forms a triad, and that is Dobrnir triad. Okay. Similarly, you see if you have calcium, strontium, barium, the atomic weight of calcium is 40, barium is 137, and average of the two is 88.5, and the atomic weight of strontium is 88, which was close, so we can consider this also as a Dobrnir triad. Okay. Sulfur, selenium, tellurium. Sulfur is 32, tellurium is 128, and the average of the two is 80, and 80 is the atomic weight of selenium. So these are the Dobrnir triad. You can find out that fluorine, chlorine, bromine, you find out the average value of the two, fluorine and bromine, you'll get the answer. Chlorine, bromine, iodine forms. Not exactly, but approximately it forms. Okay. So whenever you get this question, just take the atomic weight and you can take the average of the two and compare the atomic weight with the middle elements. Okay, you'll get it. Chlorine, bromine, iodine forms. Okay. Hydrogen, fluorine, and chlorine forms. Right, hydrogen, fluorine, and chlorine forms. This kind of example we have. Generally 0.5 to 1 we consider. 0.5 to 1, to some extent 1.2. See, actually this theory was not right. Okay. For some elements, it was exactly true. Like you can see lithium, sodium, and potassium. For some elements like sulfur, selenium, and tellurium, it is exactly true, but it is not found to be exactly correct for calcium, strontium, and barium. If you find out for chlorine, bromine, and iodine, I'll show you. Chlorine, bromine, and iodine. Right, chlorine is 35.5 atomic mass. Iodine is 127. Bromine atomic mass is 80. But the average of the two you are getting here is something around 81.25. So it is close. It is not exactly the correct value, but it is close. What is the atomic mass of fluorine? And bromine is 80. So fluorine and bromine is approximately 100, right? That's why fluorine, chlorine, and bromine does not follow Dobrnir triad. And this is the reason, because it is not valid for all the elements, right? we discarded this particular theory also. Okay. Next one, you see the third attempt was Newland's octave rule. Write down, according to this rule or theory, according to this rule or theory, if the elements are arranged, if the elements are arranged in order to their increasing atomic mass, in order to their increasing atomic mass, comma, every eighth element every eighth element had the similar properties every eighth element had the similar properties to the first one, like every eighth element will have the similar properties to the first one, like first and eighth note in music, like first and eighth note in music. Again, I'll repeat this. According to this rule, if the elements are arranged in order to their increasing atomic weight, every eighth element will have the similar properties to the first one, will have the similar properties to the first one, like the first and eighth note in music. Right. For example, you see, if I write down these elements, lithium, beryllium, then boron, carbon, nitrogen, oxygen, fluorine, and sodium. Here also we'll write down sodium, magnesium, aluminium, silicon, phosphorus, sulfur, sorry, chlorine, chlorine, potassium. Right. So this elements you see, it is exactly same as the musical note. Sa, what is the musical note? Sa, re, ga, ma, pa, dha, ni, sa. Right. You see the eighth note is again sa. We started with sa, eighth note is again sa. Similarly here, the first and eighth element, lithium and sodium, have the similar properties. Here we have same, and this thing also we have the similar properties. This is Newland octave rule. Okay. But again here, it is not valid for all the elements. Okay. All the elements could not classify. Anant, your answer is all the elements. Yes, noble gas was not discovered till then. When Newland's octave rules was given, noble gas was not discovered, right? And Anant, your answer for your question is all the elements could not be classified on this basis. Hence, we discarded this particular rule. Clear? Now the other one is Lothar-Meyer curve, the fourth one. I'll show you the graph here. Just a second. See this curve? See, what he did actually, he drew a graph between atomic volume and atomic mass. Okay. And he got the trend like this. This is the graph he got. Okay. So you don't have to draw this graph. There's few points here you see. What he observed here is the most electropositive elements, which are the first group elements you see. The electropositive elements are occupied the peak of the graph here. You see, all first group elements, lithium, sodium, potassium, rubidium, cesium, like this. Similarly, if you see the second group elements, they are here on the descending curve. Beryllium, magnesium, calcium, strontium, barium, like that. Okay. Less electropositive, right? Like metalloids, we have boron, carbon, silicon, and transition elements. They occupy the bottom part of the curve. You see the carbon here, copper, zinc here. Here you see silicon, sulfur this side, metalloids here. So this kind of trend he observed, right? So on the basis of this trend, what he concluded that the elements having similar properties occupy similar position in the curve. Write down this. According to this one, write down the elements having similar properties occupy similar position on the curve. This was actually important. Okay, similar position on the curve. This actually concludes that that the physical properties of the elements are the periodic functions of their atomic weight. Okay, that is what we get from Lothar-Meyer curve, and this becomes the basis of Mendeleev's periodic table. Okay, so write down from this curve. From this curve, we got to know that physical properties of the elements physical properties of the elements are the periodic function of their atomic weight, are periodic function of their atomic weight, and this becomes the basis of Mendeleev's periodic table. Right? Basis of Mendeleev's periodic table. Now, next you write down Mendeleev's periodic table. Few things that you should know for this, that it is based on atomic weight. It is based on atomic weight. Noble gas was not discovered when it is given. Was not discovered. Noble gas was not discovered. Next point. Mendeleev was the first scientist. Mendeleev was the first scientist who classified the elements in systematic manner. Who classify the elements in systematic manner means in horizontal rows and vertical columns. Systematic manner means in horizontal rows and vertical columns. Right. So this is the, in this we'll get horizontal rows, which is known as periods, and vertical column which is group. Vertical column which is group. Right. There are 7 periods and 8 groups in Mendeleev periodic table. Right. One more thing, each group up to 7th, each group classified into 2 categories, into 2 subgroup, that is A and B. A and B. The subgroup A, the elements are called normal elements. And these elements are called transition elements. I'll show you the periodic table. In that, I'll show you this also, A and B. Just you copy this down now. Okay, normal elements and transition elements. No. From group 1 to group 7. Till group 7, not 8th one. Till group 7. Group 1 to group 7, we have two subgroups, A and B. Not the 7th group. Okay, till group 7, we have two subgroups, subgroup A and subgroup B. A are the normal elements and B transition elements. That's why you must have seen periodic table. There it is written 1A, 2A, 3B, 4B, 5B, like that. 12B, then 3A, 4A, 5A, like that. Yes? Okay. One last point into this. The elements belongs to the same group. The elements belongs to same group exhibit similar properties. Elements belongs to the same group exhibit similar properties. Now, there are a few drawbacks in this periodic table also. The first one is the position of hydrogen was uncertain. Don't write this, just listen to me. Don't need to write all these things. The position of hydrogen was uncertain. It was not sure that where to place the hydrogen atom, with carbon, with first group, or with noble gases, right? That was the first drawback here, right? Another thing is the position of actinides and lanthanides was also not clear, right? So because of this, we have slight modification in Mendeleev's periodic table, and that we call it as modern periodic table or long form periodic table. So after this, we get, just a second, we'll finish this and we'll get a break. Just let me finish this one. 5 more minutes max to max. Okay, so after this, we get modern periodic table. Modern periodic table. We also call it as modified Mendeleev periodic table or long form periodic table. Right, a few quick 2-3 things. This is based on Mosley's experiment. Mosley's experiment, what he did, he took a metal surface, and on the metal surface, he bombarded electrons onto it. Electrons. Then from this, X-rays emits. On this process, what happens? X-ray emit into this one. And what he observed, that the frequency of the light that emits, square root of that, is directly proportional to the atomic number of the metal that we are using, the square root of this. Okay, so further, he proposed that this root under of nu is equals to a z minus b, where a and b are the constant. This is Mosley's experiment. Okay, this is Mosley's experiment. A and B are the constant. You just keep this in mind. It is not that important also. They won't ask you this. Okay, not at all important. So this was the experiment done by Mosley's, and on this basis only, he has given this particular periodic table, right? In this one, write down just 2-3 points. In this modern periodic table, we have 9 groups. 9 groups, that is the vertical column, and 7 periods, horizontal rows. 9 group and 7 period. Okay. Did you copy this? In this also we have slight modification, and we get long form, which is nothing but the present form of modern periodic table, MPT. Long form or the present form of modern periodic table, MPT. In this one, we have 7 periods. This question they ask in the exam. That's why I'm giving you all this information. This have 7 periods and 18 groups. Groups means vertical column. We have 18 groups here. Right? This 18 vertical columns or groups, we named this as first, second, third, fourth, fifth, group 13, group 14, 15, 16, till 18, like that. Okay. One last point you write down here, this last point. The elements belongs to same group, having same number of electrons in the outermost shell. Again, I'm repeating this. Elements belongs to the same group having same number of electrons in the outermost shell, and hence their properties are similar. And hence their properties are similar. Done. So these are the various theory which was given for the arrangement of elements in a proper manner, right? So after this, we'll see the periodic table and we'll discuss few trends into this. We'll see few properties. Periodic table is very important here. You must understand what are the difference we have, how do we find out the atoms, the position of an atoms. So we'll discuss that in detail, right? After the break, we'll do that. Okay, so we'll take a break now. We'll start the session at 6:35. We'll resume at 6:35. Take a break now. Okay. Yeah, take a break. Hello. Yes. Shall we start? Okay. So we had discussed about the various theories for this development of periodic table. So long form and modern periodic table that we have, okay, present form of periodic table, it has 7 periods and 18 groups. Correct? Okay. So we should understand here that how the atoms are classified here, why the atoms are placed in a given group here. That is a reason for that. Okay, so let us first understand or see the periodic table. I'll show you here the periodic table we have, and we'll discuss on this. So, okay. So if you see this periodic table, okay. So like I said, there are 7 periods, right? So you see horizontal rows, one, two. See, this is 1, 2, 3, 4, 5, 6, 7 periods here, right? In the first period, we have hydrogen and helium. Second period, we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Then third, fourth, fifth, and so on, right? So here you see this one, this two groups is 1A and 2A, which was given in Mendeleev periodic table, if you remember. The groups are classified into two subgroups, A and B, right? So this is 1A, 2A, and then this is B, the blue one, 3B, and here we have 12B, right? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 3B to 12B. This one is again A. 1A, 2A, 3A, 4A, 5A, 6A, and so on. Till here, 7A. And this one is the 8A group. Correct? So the elements here are classified in the block. Okay. You must have heard the term S block elements, P block elements, D block, like that. Correct? So the first two group, if you see the electronic configuration of hydrogen, it is 1s1, right? Electronic configuration of lithium, it is 2s1, outermost 1s2, 2s1, 1s2, 2s2, 2p6, 3s1, and then 4s1, 5s1, like this. Okay. Last electron goes into S subshell for all these first group elements. If you look at this, beryllium has 4 electrons, so 1s2, 2s2. This one also has the same configuration, that is 3s2, the outermost electronic configuration. Okay, so I'll just show you here the electronic configuration of all these elements we have done. Okay, I'm not writing it down here, you have already done, so we can go through it. Okay, the last electron, when fills into S subshell, the elements belongs to S block elements. So these elements here, all these elements are classified into 4 blocks. The first one is S block. Write down all of you. S block elements are when the last electron fills into S subshell, right? S subshell. Example here, S subshell, S block elements are, we have group 1 and group 2. Group 1 and group 2. Group 1 is this, right? The outermost electronic configuration of group 1, if you see, it is NS1. For hydrogen, is this N is the period here. For hydrogen, it is 1s1. For lithium is in second period, so it is 2s1. Sodium, it is third period, is 3s1. Then 4s1, 5s1, 6s1, 7s1. I'm talking about only the valence electron shell electronic configuration, right? Valence shell electronic configuration, outermost electronic configuration, NS1. If you talk about beryllium, magnesium, calcium, and all these elements which belongs to group 2, the outermost electronic configuration is NS2, where N is again the period of that element. Like for barium, if you try to write down the electronic configuration, the outermost electronic configuration, barium belongs to sixth period. 1, 2, 3, 4, 5, 6. Barium belongs to sixth period. So its outermost electronic configuration is 6s2. Cesium belongs to sixth period, and first group, outermost electronic configuration is 6s1. Francium, it is 7s1. Radon, it is 7s2 because it is a second group, right? So S block elements are these two. The first two groups are S block, these two, S block. Okay. Then we have 10 D block groups. From here to here, we have D blocks. And D subshell, you see, if you can, recall. Just a second, Madhumati. Just a second. Okay. So D block elements we have. D subshell can have 10 electrons. So we have 10 groups here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 different groups over here because D can have 10 electrons. So each group has one single configuration. Like this one, outermost configuration is D1, D2, D3. This one is D5, not D4, because again, half filled configuration, right? D5, D5, D6, D7, D8, D10, and D10. Right. So the exceptional configuration that we were talking about, it is possible in these three elements where we have D10 configuration. That's why this one you must remember, it is important. And here also it is possible with chromium, with the same reason. And we don't have, means the transition is that only, S to D, which is possible in the same group. So we have 10 different groups here. So 2 groups we have S block, 10 groups we have for D block. And this is the P block. We have 6 group because we have P, 6p uh, orbital configuration, right? So it is P block elements. Okay. Understood this? Correct. So why we have six group? Why we have six group? Because we have a P block, and P can have six different configuration. Okay, seaborgium is not in this Kenshuk. It has atomic number more than 100, 106. That is not mentioned here. You can see it is still 103 only, right? That is not given in the periodic table, not required. Okay, till 103. Seaborgium is 106 atomic number, if you see. Okay, so this is the different groups we have. First of all, the classification is like this. We have one more thing, that is F block element. You see here, this atomic number I'll write down. You must have the idea of the entire periodic table. Just a second. This one is 56, right? 54, 55. This one is 56 atomic number, barium. Then it is lawrencium 57. It is 57. And then it is hafnium, it is 72. So there are 14 elements not present here. This one is also, this one is 58 radium. And then this one is, oh sorry, it is 88, not 58. This one is 88. And this one is actinium 89. But this one is 104, 104. Again, 14 elements are not present here. So after lawrencium, what happens, you see, no, so not lawrencium, lanthanum. This is lanthanum La. After lanthanum, electron starts filling into 4F subshell. And that 4F starts from cerium to lutetium it goes. If you count this, you will have 14 elements here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. After 89, we have 90 to 103. This goes into 5F series from thorium to lawrencium. This is 90 atomic number, and lawrencium is 103 atomic number. So these groups here, these are F block elements. F block, because the electron goes into F subshell here. Okay, so it is not that important. The only thing you have to keep in mind here, okay, for F block, we have two series here, 4F series, which we also call it as lanthanides. Lanthanides starts with cerium, atomic number 58, and it goes to lutetium, atomic number 71, 4F series. Another one, we have 5F series, which we also call it as actinides. It starts with thorium 90 and goes to lawrencium 103. Always keep that in mind. Lanthanides won't start with lanthanum. Lanthanum is not a part of lanthanides. Okay, lanthanides is a series of elements, starts with cerium and goes up to lutetium. Actinides, actinum is a not part of actinide series, starts with thorium and goes up to lawrencium. Understood this? Otherwise, if you look at this electronic atomic number here, hydrogen is 1, helium is 2, 3, 4, 5, 6, 7, 8, 9, 10. 11, sorry, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, and so on it goes. Till 57, it was fine. But after 57, we have here directly, we have 72. It is not 58 here. Because after this, 4f subshell comes into the picture and electron starts filling into 4f subshell, which we are not showing over here. It is here. And same thing we have here also. Okay, this is one thing. Another thing you see, this 3D series, it 1, 2, 3, this is the fourth period we have. It is not the third period because scandium, the electronic configuration, if you draw, it is argon, that is 18. Then we have 4s2 3d1. So the period is fourth, the outermost shell. It is fourth, it is not 3d. 3d is not the outermost shell. Outermost shell is 4s. So period is fourth, it is not the third period. So the D block elements starts in fourth series, not in third series. Okay, this is also you have to keep in mind. So this is how the classification of elements are done. We have S block elements. The last electron fills into S subshell. P block elements, last electron fills into P subshell. D block elements, last electron fills into D subshell. F block elements, last electron fills into F subshell. Okay, lanthanum is not an F subshell element, it is D, it is not F. Okay, if you look at the electronic configuration of boron, 1s to 2s to 2p1, right, P subshell. Carbon, 1s to 2s to 2p2, P subshell. 1s to 2s to 2p3, 1s to 2s to 2p4, 2p5, 2p6. Okay, helium is present in P block, but the last electron goes into S subshell. For helium, it is 2s, sorry, 1s2. It is not 1s to 2s to 2p1, right? But helium is placed here because it is an inert gas and its property is very much similar to the properties of other noble gas, and hence it is placed over here. Right? So there are some modifications, but more or less the pattern is that only. Did you get it? Tell me guys, yes, any doubt in this? Yes. Now the other thing that you should know about this periodic table, I'll again take one more image. Mm. Okay. The other thing is what? The outermost configuration I'm writing down here. The outermost configuration of this, it is 1s1. It is the second period, so 2s1. Third period, 3s1. Fourth period, 4s1. 5s1. 6s1. And 7s1. This I have written for group 1, only for group 1. Right. So if you know the position of the element, you can directly write down the outermost electronic configuration. You don't have to draw the entire electronic configuration. Similarly, for group 2, it is beryllium belongs to second group, 2s2. Third period, 3s2. Fourth, 4s2, 5s2, 6s2, and so on. Okay. Hydrogen, the atomic number is, you see, it is 1, this is 3, this is 11, this is 19, this is 37, this is 55, and this is 87. Okay, now if you look at the difference here, it is 2, 3 minus 1, 2. This difference is 8. This difference is again 8. This difference is again 18. This is 18. And this is 32. So if you know this difference for group 1, if you look at this number, 2, 8, 8, 18, 18, 32, these numbers are called magic number for group 1. Means usually what happens, the elements which are there on the top, we know the atomic number for them, but the lower elements atomic number we don't memorize, okay, because we don't use it very frequently. So if you know this number, you can find out the atomic number of any elements in the bottom, right? Just suppose you know hydrogen, you don't know for potassium, for example. So hydrogen we know 2, you add hydrogen, you know 1, you add 2 into this one, 3, then lithium, add 8, 11, then potassium, again you add 8, 19, potassium, 18, rubidium, cesium, francium. Like this we can find out, right? So for group 1, the magic number is this. But here what happens, beryllium is, you see here, beryllium atomic number is 4, magnesium is 12. So for group 2, the magic number is what for group 2? Could you tell me? The only difference is this atom we do not have on the top. It is 4, 12, 20. So it is 8, then 8, then 18, then 18, and then 32. This is the magic number of group 2. Right. So first atom is not there. So just will remove the initial, that is 2, and everything is same. We can find out like this. Same thing is valid here also. Boron is 5, right? Aluminum is 13. So 5 plus 8, 13. 13 plus 8, that is 20. Just a second. 5 plus 8 is 13. 13 plus 8 we cannot write here, because here we have 10 D block elements present here, right? So for group 2, it is this. If I write down for group 13 to group 17, 13 to 17, this would be 8. I'll write down here. This is 8. Then this 8 we have, plus we'll write 18, and then we have again 18. Next we have 32. Right, you can see this 72, 73, 74, 5, 6, 7, 8, 9, 10, 80. This is 81. 81, 49, correct. So this is the, from group 13 to group 17, the magic number is 8, 18, 18, 30. That is what you need to memorize, nothing much. Okay, so if you know these differences, we can easily find out the atomic number of lower elements. Not, you won't require it most of the time, but sometimes in the exam, you never know, you must have required, you may have the information of it, right? And you need for this to solve the question. Actually, also what happens in the exam, sometimes they will give you the atomic number, sometimes they won't give you, right? So you should know this, right? How to find out. One last thing, for noble gas, if you see, the difference is what? This is 8 here, 2, 10, this is 18, sorry, 8, then this is 18, then again it is 18, and then it is 82, 32. So for noble gas, it is 8, 8, 18, 18, 32. For group 2 and group 18, it is same. That is what the trend we have. Okay, so we have 2 S block. Okay, we have 6 P block groups, and we have 8 D blocks. 2 F block, we have 2 F series. Okay, 4F series and 5F series. This is the classification of elements in the periodic table. Did you get it? So I would suggest you buy a periodic table. Okay, it is available online. You can buy this, right? And you keep on revising like this. Once you revise twice and thrice, right, you will be memorize it. You don't have to do it again and again, right? But just some analysis, some practice requires here. Okay, it's very important, right? Okay. Now, the next thing you write down: how do we predict the position of an elements in periodic table? Okay, so I'll just show you this, how to do this. Okay, heading right down. Prediction of period, then group, and then block. In which block the element is, in which period the element is, and in which group the element is. Okay, the first thing is, generally what happens, electronic configuration would be given in the question. Electronic configuration. If it is not given, you can draw it. Right, you can draw it. So period for the given electronic configuration would be, it's very simple to identify. Period, you won't have any doubt and you won't get wrong answer into. You can easily determine the period of an element. Period is the maximum number of n. That is the principal quantum number. If the quantum number, if electronic configuration is given 1s2, 2s2, 2p6, 3s2, 3p6, you just see the maximum value of n, that would be the period of that element. Okay, block I have already told you. Block is what? Is the subshell, which takes the last electron. Which takes the last electron. Right? Group, you have to be a bit careful to find out the group of the elements. So if it is S block, sorry, if it is group 1 or group 2, so for S block, what we do, because we can find out the block easily. So for S block, the elements belongs to group 1 if its configuration is some inert gas configuration, NS1. We have seen this. The elements belongs to group 2 if the configuration is some inert gas configuration and the outermost is NS2. Okay. If it is P block, then the group would be 12 plus the number of electron in P subshell, outermost P subshell. That gives you the group. Third one. If it is D block, group is 2 plus the number of electron in n minus 1th, means the inner shell, not the outermost shell. N minus 1th D subshell. Number of electron in n minus 1th D subshell. And the last one, if it is F block, fourth one, if it is F block, the group is always 3. For F block, you don't have to worry about, it is always 3. Let's see this, the periodic table once, you will get it. In this periodic table, you see the F block is here, right? Is here. It is in 3, third group. These two are F block, which is this written over here. Both belongs to group 3. So F block, it is always 3, third group. Did you understand this formula? Why these formulas we have? See, I'll tell you. Just you focus on this formula, P block. 12 plus number of electrons in P subshell. Right? Why this 12 we have here? That's the question, right? So you see this periodic table. This is the P block, right? And P block starts with group 13, then 14, 15, 16, correct? Why group 13 we have? Because 12 groups are already present here, 2 S block and 10 D block. That's why the number of electron in P subshell plus this number, that is 12 from here to here, gives you the group here. Yeah, that's right. Okay. Similarly, if you see D subshell here, why we have 2 plus number of electrons in n minus 1 of D subshell? Because D starts with third group, right? And before this, we have 2 group already present. So 2 plus number of electrons in D subshell. Clear, Shraddha? Right. So if you have the idea of periodic table, if you could visualize this easily, right, you can easily identify these things, right? But formula actually helps you sometimes because in the exam you'll have pressure, right? So for that only we have formula. But if you can understand the formula, right, you don't have to memorize it. You can easily write down the formula. Now, based on this, we'll see some examples. Tell me the period, block, and group of these atoms whose electronic configuration is given. So first one, the electronic configuration is 1s2, 2s2, 2p1, Second one we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. Third one is we have argon 4s1, 3d5, xenon we have 4f7, 5d1, 6s2. Then we have krypton 4d10, 5s2, xenon 4f0, 5d0, 6s2. For this, you need to identify period, then block, and then group. Yes. Yeah, actually, I was on the call. Uh, one of my friend's dad, he found to be positive. That's what the news I got. I was on the call. Sorry. Anyways, so all of you are done. Can we start the discussion? Okay, fine. See, the first one is very simple. Period, if you want to find out, is just the maximum value of n given in the electronic configuration, correct? So period is 2 here. Obviously, the last electron goes into p subshell. Block is p, and the group is what? The formula we use 12 plus the number of electron in p subshell, outermost p subshell. So that is 13. Okay, this one. What is period here? It is 4, the maximum value of n. What is the block? Block is D. Last electron goes into D subshell. And for D block, the formula is 2 plus number of electron in n minus 1 addition. See guys, try to understand here. The outermost shell here, it is 4th shell. It is not the 3D shell. 3D subshell is present in 3rd shell. 4th shell is after 3rd shell, right? So outermost shell is 4th. It is not 3D. When you try to take out the electron from this, electron first comes out from 4s shell, from 4s subshell. It is not 3D, correct? So outermost is 4. That's why in the formula we have n minus 1 d subshell, right? So n is 4th, n minus 1 is 3. So 3, d has 2 electron. So 2 plus 2 plus 2, that is 4th group we have. No doubt in this? Okay, this one I'll discuss in the last. Let it be this one. This one also will discuss in the last. Let it be this one. This two will discuss first. Okay. 5s2, 4d, 10, right? So what is the period here? The period for this one, yes. So the period for this one is 5. It is 5th period. Okay. What is the block? It is D block. No, it's not S. Again, you see, it's the same thing. 5s, I have written it later after 4d, but it fills first. 5s fills first. No. What is the n plus L value of this? N plus L value is 5. Yes or no? N plus L value is 5 here. This n plus L value is 6. So obviously the energy for this one is lesser. This should fill first, and then will electron goes into this one. Akshar, just a second. You concentrate on this. We'll discuss the second one in the last again. Okay. Did you get it, guys? It looks like simple, but you'll make mistake in this kind of question. Okay, I have written 5s in the last. It doesn't mean that the electron goes into the 5s subshell in the last. If you have this kind of confusion, you can check n plus L value and then you can think of it, right? So n plus L value for 5s is lesser than to that of 4d. That's why the electron first goes into 5s and then into 4d. So the block is D block. And then the group is what? 10 plus 2. It is 12th group. No doubt in this. Tell me, yes or no? Yes? Are you getting it? Last one you see, there's no electron in 4f and 5d. Period is 6, S block, and it is the second group. Simple one. Okay? This one, if you look at this atom is chromium. This atom is chromium, and for chromium and copper, we have exceptional configuration, electronic configuration. So if you apply the rule, D block rule, you'll get it wrong here. I'll show you how. First of all, the period is 4, right? Block is D, you can say. But if you find out the group would be 5 electrons plus 2, it is 7. But this one is not correct because 7 is not the electronic, is not the group of chromium. I'll show you the periodic table. That's why periodic table is very important here. If you have the understanding of it, you see what is the group of chromium? It is 3, 4, 5, 6. Chromium is in 6th group. It is not in 7th. Okay. So this formula that I have given you here, it fails over here because this chromium has exceptional configuration. So whenever you have this exceptional configuration, you have to be a bit careful, right? Answer for this one is 6. It is not 7. Did you get it? Yes, guys, please respond. Clear? So whenever you have this kind of configuration, you must be careful, right? The normal formula we cannot apply. Could you tell me whatever the electronic configuration we have here? First of all, the period is 6, right? The period is 6, and the block is, what is the block here? It is F block. Again, you see you made the mistake here. It is F block. Very good, Akshat. Okay. No, 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 no. I have shown you the periodic table so that you can understand it. Just the confirmation that the chromium does not belong to 7th group, right? What I'm telling you that when you have D5 configuration, see, just a second. Let us first understand this. We'll get the previous one also. Okay, this one is F block. Could you tell me the atomic number of this one? What is the atomic number? 7 plus 2, 9, 9 plus 1, 10 electrons. What is the atomic number of xenon? Xenon is 54. 54 plus 10 is 64. So atomic number is 64, right? Now I'll take the reference of periodic table again to make you understand. It's not like you require periodic table always in the exam, right? You see 64 is the number we have. So we have 57 we have here. Lanthanum is 57. And then 58, 59, 60, 61, 62, 64, 62, 64, right? And I have already given you that the F block, F series starts with cerium 58 to lutetium 71. You have this information. It means the 64, the atomic number that we have, it goes into F4F series, that is F block. Okay. Now the question is why we have here 5D1 configuration, because F orbital can accommodate 14 electrons, then why one electron jumps into 5D? Again, the same reason, 4F8, 5D0, 6S2 is not the stable configuration. This one you see, 4F7 is the half filled configuration like 3D5. We have 4F7. That's why to get this configuration, one electron jumps into 5D and the configuration is this. So this one is F block elements. Here also, if you use the formula, the normal formula, you'll get it wrong because it is not 5D, it is F. It has exceptional electronic configuration. And whenever the block is F, the period, the group is always 3. There is no doubt for this. Tell me your doubts now. Akshat, did you get the second one? I guess yes. Tell me, any doubt in this, guys? So one simple hint I'll give you here. In this kind of question, I have already given you the formula, that is fine. But whenever you see this D5 configuration, D5 configuration you see, D5, D10 configuration you see, F7 configuration you see, then you have to be a bit careful while using the formula. We'll do this again, Kirtana, just a second, right? So must take care of this. Whenever you see this configuration, you have to be a bit careful, right? While using the formula, okay? Must revise that periodic table, the entire periodic table, whatever we have discussed, how the atoms are arranged, the outermost electronic configuration and all. You'll have a better picture of it. Yeah, so we'll discuss again the fifth one, okay? So the fifth one you see, I have written 5s2, 4d10. 5s2 I have written in the last. Actually, if you write down the electronic configuration here, first the electron goes into 5s and then it goes into 4d. I have written it in the last just for you to, like, you will get questions like this. You'll write this 5s in the last so that you'll make mistakes in the exam. I can arrange this 5s 4d whatever I want. It is not about the electronic configuration. It is, you need to find out the period, group and block here. So it's not like the electron fills into this orbital in order, like it goes into 4d first and then 5s. Since I have written 5s in the last, that is not the reason. Actual thing is this, while writing down the question, I have replaced this. I have exchanged the position of this two. So we'll have this, right? No, in the configuration, it is not, that's what I'm telling you, Shraddha. It is not for, if they ask you in the exam, write down the electronic configuration, you have to follow the order, right? But since it is not for electronic configuration, so I have just rearranged it here and there to make you confused. You understood this? Right, so it does not mean that 5s is written in the last, hence the electron goes into 5s orbital first. Proof I have given you. You calculate the n plus L value of the two orbital. Obviously 5s orbital has lesser n plus L value than 4d. Right, so obviously electrons should go into 5s first and then into 4d. Correct, so this kind of understanding you must have. Did you get it, Kirtana? Okay, so I would request all of you guys, if you can get periodic table, get it ASAP, okay, and do all those things which I have done in the class. Okay, if you have the understanding of periodic table, right, if you can visualize this, then you can understand the entire chemistry very, very easily. It's not like we use periodic table in all the chapters, but yes, you never know when you require the the understanding of the position of the element. So you must have the better understanding of, good understanding of periodic table, right? So you must buy that and just go through it. No, just till zinc you should memorize the atomic number till zinc, hydrogen to zinc. More than that is not required. And anyways, you have the understanding of that, how the what are the magic numbers and all. So if it is required in rare case, you can find out with that. But till zinc you must memorize. How do we determine it is 6, especially in the third sum? 6, what is 6? 6, where is, acha, this one. This one, like I said, you have to be careful when you have this configuration, D5, D10 and F7. Then you have to think about it, right? Like logically what we have, 3d5 has 5 electrons, 5n plus L value, but 4s has 4n plus L value. Why not 4s orbital gets filled first completely, right? And why electron goes into 3d? It should be 4s to 3d4. but that is not happening here. So my suggestion is, whenever you have this kind of confusion, you just check n plus L value. Accordingly, you can say the orbital which has lesser n plus L value, electron goes into that orbital first. Which has maximum n plus L value, that would be the last orbital to be filled, right? But when you have this configuration, D5, D10, F7, then you have to think over it, like how to do, what is possible and all, right? Like I said, 4f orbital can have 14 electrons. So why not this electron goes into this one, right? 4f8, 5d0, 6s2. It is not happening because it has an exceptional configuration in order to get more stability. That's why it is happening. So little bit of, understanding is required, practice is required, then you will get it. Yeah, I'll do this. I'll get some more example. We'll discuss onto this one so that you will have a better understanding of it. But I would suggest at least this fourth, fifth, third, fourth, fifth, and sixth, this 4 question, you do it on your own, and periodic table you must revise. Okay. Fine, guys. So we'll wind up the session here. Right. Next class, we'll start with some more example, and then we'll discuss the another concept into this. Thank you so much. Take care.